Good morning, everyone. So today we'll be starting with chapter 3. In earlier two chapters, we have seen that some of the concepts of the defined reservoir, and in the second chapter, we have seen some of the methods for gas in place analysis and different consideration for error and how can you rectify those errors. Today in this class, in this chapter, we'll be just discussing the measurement technique, the disruption measurement techniques for the disruption dissolved gas content, and some related issues as you are going to estimate the gas content evaluation. Okay. Now let me tell you that this is the last chapter from this note. So after this note, I'll be giving you only or discussing some of the papers only of related to your CBM work, CBM concepts. Okay. So this is the last theory chapter of this from this note. Okay. From tomorrow onwards, I'll be discussing the papers and some of the important papers and the conclusions and the findings for your better understanding, and I'll be also uploading after this class. So let's start with this, and before starting, let me tell you that I have already informed in the group also that by first week of the March, your total theory classes will be done. And as we have also got the mail yesterday, maybe you have also received that after 12 or from 12th onwards, you will be having laboratory classes. You will be too busy with the laboratory classes and other practical issues. So what I suggest that date 8, 9, 10, although I have kept 3 dates, but I think 2 will be sufficient to take your viva. And for this viva, whatever discussion has been made in the class, except for the papers I'll be loading, okay, except for the papers. So whatever discussion is done till today's class, that will be included for your viva. The papers, whatever I'll be discussing, that will be included in the end sem exam. Okay, I'm again repeating, for the viva, total syllabus will be all the notes to today's class. For the end sem classes, whatever paper I'll be showing, that paper will be incorporated there. Okay. There was some problem in the network. Can you hear me correctly what I have mentioned?
Yes, sir.
Okay. Or else I'll be also notifying in the WhatsApp group. So let me just start the class today. Now, for this class, the gas content evaluation, you know that for this gas content, there are 2 things you need to do very meticulously, okay? And the accuracy of your total gas content will depend. Now, remember that I am talking about the gas content, not the gas in place. And I hope that you understand the 2 differences. Gas in place is the in situ gas content, whereas the gas content, whenever I am talking to the gas content, I am going to discuss it with the laboratory point of view or the taking the sample from the underground and doing on the surface. Okay, so that's why we need to be careful about the two main concepts. First is the perform the gas disruption measurements as at a reservoir temperature or on conventional core samples. So you have to do the disruption measurements preferably at the reservoir temperature to calculate the dissolved gas content, and then estimate the total gas content of each sample using the direct method of the loss gas content procedure. So loss gas procedure you already have seen in the earlier note. So you have to calculate the total gas content based on the lost, then dissolved, and the residual gas content. Okay. So based on these 2 calculation, you will be able to see at how much information you are getting, and you have to correlate that also. Okay. So in the starting, you can see that the total the total steps is required, that is also shared with you. This table 1.1, table 3.1 is giving the total steps of the summary of the core desorption procedure. Okay, this is very easy. Okay, it is not a big deal to understand at this point. So you have also some idea about the coding and taking the samples. Okay, so you will be able to understand. So this is the exact method of, this is the direct method by the desorption canister testing. And you can see this is your figure for desorption canister. Let me just uh, reduce the resolution. Yeah, so now you can see this is our desorption measurement procedure. This is the schematic diagram showing the main concept of the desorption canister and their parts. Okay, this is the parts. You can see that it is a aluminum container. Preferably, it is an aluminum container. If you read this text, they have discussed all the construction fittings and the process for evaluation. Okay, but I am going to give you a gist idea, and for you also, for your knowledge purpose, you will be also reading it once and having a brief idea. Detailed idea is not required. Okay, so that if anybody asks you that how you are going to measure the dissolved gas content, you will be able to tell. Okay, so this is the aluminum gas container. Okay, and with some special threads fitting. You can see inside this there is a rubber jacket is also giving. Okay, rubber jacket is also there. There is a pressure gauge varying with some pressure readings. Okay, there is a hose pipe, there is a valve is going to allow the these without this valve you will not be able to open. Why? Because once you have put this coal sample into it, it will give you some it will release some gas. That gas will be having some pressure. Until unless you are going to reduce that pressure to zero, you will not be able to open this canister. That's why this hose pipe is very much important, or this hose bar is important. Okay, and there is the lead assembly by which you are going to tight it. There is a inbuilt o-ring. How to discuss with you the o-ring? If you have seen the pressure cooker, okay, or if you have seen the pressure cooker, there is a rubber o-ring, a rubber circular ring surrounded the periphery of the upper cover. Okay, so you can assume that as a simple o-ring. Only the difference is that it will be of varying size and with good quality, because it is going to be used in the underground or in the other rock desorption analysis. So that is the concept of the o-ring. Most of the cases, the instrument fittings are having o-ring so as to prevent the leakage, because otherwise air can pass through any openings. Okay, now this is for the gas, so obviously the o-ring is very important. Okay, the dimension and the material. Now what you are going to do? Very simple. By the core barrel, you will be taking the core, generally 1 feet of core. You are going to take it. You are going to put it into this. You are going to surround it with the rubber sleeve, and then you are going to put it into the. And after you are going to the diamond core bit is cutting that core sample. Okay, it is within this core barrel. Now, when you are going to take this core barrel, until and unless you are taking out this core barrel, all this core barrel drill assembly and the reservoir, the core is within the reservoir temperature pressure condition. But the moment you are going to take it out into the surface, then its pressure and temperature is going to vary. Okay, so the moment you are going to take out the core barrel, you are going to open this core barrel. The moment you start opening the core barrel, the resorption will take place, because you are actually going to zero the pressure. So the quicker you are going to transfer the coal sample to the resorption canister, your stopwatch has to be pressed, and that is the time you are going to incorporate into a lost gas estimate. Otherwise, you are going to get substantial loss in the lost gas estimate. Going to delay from the after opening the core barrel. If you are going to delay, hello. Sorry, I am having a
Yes, sir.
phone. हाँ जी बोलिए। हाँ 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 मेरे ऊपर में वो अंकुर सर भी है, मैं उनको बोल के रखा हूँ, आप आइएगा तो दोनों का एक साथ हो जाएगा। ओके ठीक है, थैंक यू थैंक यू। सॉरी आई वाज connection. Hello? Am I clear now? Am I clear now? Can you hear me all?
Yes, sir.
Okay, okay. Sorry for that call. The data center was calling me for internet connection. So sorry for the disturbance. Yeah. So if you see this structure, if you see this structure of this assembly, okay, this is the sample you are going to. The moment you are going to take out the sample from the core barrel, the start of the dissolvation, because the pressure is going to zero, so the gases will start to dissolve. So you have to transfer the core sample from the core barrel and quickly to this dissolvation canister, and you have to seal it, and then you have to put this valve into the off position so that the gases will dissolve. These gases will dissolve, and you will see the deviation into the pressure gauge. After, you will see that after depending on the coal type or the coal composition, and depending on the gas content, in situ gas content of that area of that coal sample, obviously after within 1 week, sometime it will take within 1 week, sometime it will take only some higher days, okay, when you will see that there is no such deviation of this pressure gauge by consecutive 1 or 2 days, then you will be able to understand that okay, total desorption was about to take place, it is already done. So then by this now we are going to measure this gases, amount of the gas that is dissolved. So how we are going to do it? You are going to do this desorption, you are going to feed this with the desorption other desorption container, okay. as you can see as you can see that after you have got this measurement, you have to fit it with the fitted this there is another structure of the fitting arrangement of the pipette and burette and the other fine lines, so that you can get the dissolved gas amount by the water displacement technique, just like the normal laboratory experiment of the gas collection. And there is a jar, it is a these bullets are having graduation, so that so that you can see how much water is being displaced. So similarly, space is actually the volume of the gas that is dissolved, okay. For this thing, you have to ensure that you are going to perform this experiment at the reservoir temperature and the pressure, okay. If not you are going to take out this gas at the surface temperature, and then you have to change it, you have to correct it with the reservoir temperature and the pressure. Because if not, you are going to do this calibration, do this correction with respect to the reservoir temperature, pressure, whatever gas content you are going to calculate, idea or exact value of the in situ gas content, okay. Because in case of in gas in place analysis also, we have seen that you have to do everything based on the reservoir temperature, pressure, okay. So that's why we are going to do this in case of in situ temperature and the pressure condition. Now, before you are going to do this, if you read this, they have explained in a very nice way, okay. I hope that if you read it only once, you will be able to understand the process. That is not a big deal, and you may need to prepare a note only about 5 marks question. If I ask you to discuss this disruption tensor test, it will be of, suppose you can write that it is as a 5 marks question, okay? And so you have to discuss the salient features. You don't need to draw the figure, and you need to give some paragraph, okay, discussing the main points, the assumptions, what are the main things we are going to do, and some considerations, some assumptions, and the errors, okay. Now here, whenever we are going to put the sample into this reception canister, we are actually going to put the rubber slip first, okay. The rubber slips are given. Why? Because if you are not going to put this rubber slip, then obviously whatever shock you are going to get by this reception canister, it can transfer the shock to the sample and it can deteriorate the sample, okay. So the more pieces of the sample will obviously increase the disruption by increasing the surface area, but the calculation will may be having some problem, and you may lose some pieces of the core also. Second is that the rubber sleeve will also hold the sample. It will take the sample as a whole, and even if there's a drill breakage, or there's a shock breakage, okay, of the sample, it will be remain intact by the core sleeve, by the rubber sleeve. Then obviously if there is a chances of the chemical fluids present, depending on the drilling fluids, if there is a chemical fluids that are going to mix with the sample, the rubber sleeve is going to separate that fluid from actually mixing with the sample, and thereby not damaging the sample, okay, or affecting your gas content, dissolved gas content. And finally, whatever the sample information you are having as per the reservoir condition, suppose you are having the sample moisture, okay, the in situ moisture, the in situ texture, and some of the drill cuttings or some of the other code you are having, so there will be no such mixing, okay. So you can preserve the weight also. There will be no such loose pieces. You will be, yeah, otherwise it may miss them, okay. And so it may vary the quantity you are going to present in SCF per ton or CC per gram in unit mole, okay, unit weight. So for this, we are going to provide some rubber sleeve, okay. Now, water displacement technique is very common. You have also analyzed it in the laboratory by some other chemical testing or by some other analysis. So this is very simple. So I'm not going to discuss this in detail. Now, you are going to measure this lost gas, and as you know, that here is also a graph. Let me show you the graph also. Uh, Yes, this is the graph of the lost gas. Okay, you are going to measure this much of the with your stopwatch. You are going to measure this is as the gas dissolved data. So you will be seeing that the pressure is going to or the volume of the gas is going to reduce, and finally it is going to be constant. But if you are not going to get this initial stopwatch point when you are going to press 0, the backward movement, how much you are going to extend backward this graph, this will give you the very high error, okay. The chances of the error for this lost gas constant is very high, very significant. So you have to be very careful, okay. That's why this initial 0 pressing time or the start time is so important for the calculation of the lost gas, because you can see that the graph is very steep in the initial stages, okay. So if you are going to if you are not going to press the time 0, and by this time you are going to press, it is already 4 or 5 seconds gone, then maybe you will be getting a somewhat flatter graph, okay. And that flatter graph will give you very much less. You can see that 50 or maybe 100 SCF per ton, if this is in SCF per ton, yes, if this is SCF per ton direct method gas volume, so obviously this much of the gas content you are going to lose, okay. So this much is the error, so you have to be very careful. Now, after this residual gas is done, you know that there is a residual gas. Okay, how you are going to this residual gas? You are going to take the sample, you are going to take out this core, and it is observed that the residual gas content is also significant. It's approximately 15 or somewhat close to 20% of all the total gas content. So obviously you need to calculate the residual gas content also. Okay. Now, whenever you are going to take out this core sample, after all the desorption has been done, you have calculated, you have estimated the dissolved gas content. When you are going to take out this coal sample, removing from the desorption canister, you have to actually divide in two parts. Okay, you can see this discussion is also given in this subsequent paragraph. You have to split these samples in the half longitudinally. Longitudinally means axially. One half will be kept preserved for some other analysis, and other half you have to place it into the ball mill. Okay, and ball mill is having some steel balls, and then you have to crush the sample. Okay, you have to crush the sample so that it is forming some powders, and then again you are going to get those powders, and then you are going to get the residual gas content. Again you are going to fit it into the chamber, and then by the pressure gauge or by the volume gradation, you will be, whatever gas is going to be coming out, you can again take the water displacement technique, and you will be able to know the how much residual gas content is coming. It is very less, as you can see, it is only 15 to 16% of the total gas content. So depending on your total gas content, this value may be somewhat very much difficult to notice. Okay, so you have to wait patiently. Now, when you are going to do the crushing, what is the main thing you are going to do? Actually, when there is a chunk of the gold, suppose you are going to take a cube sample. A cube is having 6 surfaces, so you are having only 6 surfaces. But the moment you are going to break it in two parts, then you are having actually two rectangular surfaces of 6 and 6. So now there is a 12 surfaces, and now you can see that as you are going to increase the surfaces, so now the gases can escape to the atmosphere by means of these pores and the fractures. Okay, so when you are going to degrade the sample from the core or the slab sample to the powder sample, you are actually crushing the sample and thereby increasing its surface exposure. So the more is the surface exposure, the more is the amount of the desorption or the rate of the desorption. Diffusion, which is called the diffusion. Diffusion is also increased by the moment you are going to crush the sample. There is a three types of diffusion. One is the bulk diffusion, one is the Nernst diffusion, and one is the intermolecular diffusion. Okay, so if you are going to do the particle, do the molecule part, and for each molecule, if you are going to consider the coal molecules with the gas molecules, then you can easily understand that with this case, for the core sample and for the powder sample, for the powder sample case, obviously the sizes as being very much reduced, it will take very quicker time, it will take very quickly, the total amount of adsorbed will be also higher, the rate will be also higher, and the equilibrium will be reached much earlier, because the total amount that is supposed to be dissolved from this powder sample is already being done within the first few hours, or maybe within 1 hour. Okay, so that's why we are going to crush the samples. Now, whenever we are going to do this sampling, this powder sample, the residual gas content what we are going to collect, again it has to be corrected for the temperature and the pressure condition, and that's why we have to do the same correction because of the temperature, reservoir temperature and the pressure. Now, whenever you are going to measure this residual gas content, again you have to see that whatever which base you are going to choose. You can choose reservoir basis, as receipt basis. You can choose air dried basis, or you can choose DAF basis. And by this time you know all of the basis, okay, the depth basis or the air dry basis. So that's why it is important to know the representation at which part. Okay, generally you have seen earlier that we have taken first the air dry basis, and then from air dry basis to the inorganic content or the organic content basis, and from there we have done the basis as the in situ gas basis, okay, or in situ gas content basis. So whatever we are going to measure, the basis has to be remembered very carefully, okay. So this is the total process of the residual gas content. Now, whenever you are going to do this measurement, okay, you know that when you are going to do this desorption, you know that during qualification process, it is mainly the methane, but not only methane. Okay, so if there are different type of gases that are going to be within this reservoir, so you have to have the idea that what is the total fraction of the gases. Okay, that means in the 100% it is not pure methane. So what are the other gases? Because if you are going to calculate the gas content, if you don't know that how much is the methane and how much is the carbon dioxide or how much is the nitrogen and other gases, so you may have some error for the gas content measurements for the methane only. Okay, so for that reason you have to understand the different gas fractions also. That gas fraction can be measured by the gas chromatograph. It is not mentioned here, but let me tell you, you may see that there is a gas chromatograph, portable smaller gas chromatograph present in our laboratory in NIT Rourkela. It is present in, I think, Tripathi Sir's lab. So if you see that the gas chromatograph is based on two principles: the FID detector, flame ionization detector, and the thermal conductivity of the gases. Okay, what we are doing, we are going to put a inert carrier gas, and based on that, we are going to insert the sample of the gases. Okay, so based on the inert gas behaves like a medium, and which is give you the base for the analysis. And then when you are going to put the sample mixture of the gases, depending on the different thermal conductivity of the gases, you will be able to see the peaks. Okay, you will see the graph, and the area has computed other lower the peaks. Okay, the area with the graphs for each of the gases. From there you will be going to correlate with the calibrated calibration of the instrument, and from there you will be able to know about the different gas composition in a gas mixture. That is the principle of the gas chromatograph. Okay, so no detailed explanation is required at this point. Next is the sample combustion. Now, sample combustion is obviously for the coal. You know that the sample combustion, whenever you are going to take the coal sample, you have already seen that there is a lot of heterogeneity and anisotropy present in the underground. Okay, so now depending on the sample you are going to collect, you have to first ensure that that sample will be representative of your total reservoir or your total borehole, and it should be able to take all the variation within your sample. Okay, you should be able to consider all the variation. If not, then suppose that if your three coal samples you are taking, and this is totally varying in the composition, okay, but you are not going to consider the three samples, you are going to consider only one samples, then you will be having some problem for the error of the estimation. Okay, so in that case you will be having some underestimated results or overestimated results. You have to take the average results, okay, compared to the your sample. आप ऊपर से घूम के तब तक मैंने क्लास खत्म हो जाएगा, ठीक है, मैं बोल दिया हूँ यह है. So if this sampling has to be done proper, then you will be able to understand that whatever calculation is being done, whether it is representative or not. Okay. Next is that you all know that depending on the sample, depending on this maturity, depending on the sample and the maturity, the coal type, the deposition and the qualification process will change. And so whatever the interbedding lying within the coal seam or within the coal bed, that is going to differ. Okay, so that is obviously going to differ because of the qualification. You know that depending on the stages of the qualification, there are some metamorphism is going to change place, and there is some constructional, or there is some compositional changes within the coal sample, because it is totally based on the deposition and the transformation and the transfer of the fluid, and under the process of temperature, pressure, and the barging processes, it is going to evolve into some higher grade. So for each of the stages, the coal is the defined coal sample, depending on the depth, obviously, depending on the depth, it will be having a definite variation of the composition. So then, depending on the composition, you need to check whether you are going to take the samples, whatever samples you are going to take, it is representative or not. Let me show you this figure they have taken from the field analysis. You can see that they have taken some data, density log data, okay, of coal interval. You can see this is the density data. The second graph is for the analysis of the layers, okay, coal, shell, and the tungsten mineral and the coal. The third is for the X-ray radiograph to see the bands, to see the layers more prominently, and obviously with these layers, they are also going to get the density profile by the gamma signature, and finally they have also seen a photomicrograph. Now, with this, what is the purpose to showing you all this? With this information, you can see that how you should interpret the coal sample, okay, or whether it is at all the coal sample or not. Because whenever you are going to take the samples, depending on the drill cuttings, there is a much more probability that you are going to mix it with some other materials, other organic, inorganic, or other metal components, or other different rock type. So it is just act as an impurity to the coal sample. Whereas if it is totally coal sample, then depending on the maceral composition or depending on the coal bands, obviously its density, its maturity is going to change. So it is obviously at a particular section or in a particular zone, you are not getting a homogeneous coal sample, it is heterogeneous. So depending on that maceral, depending on that internal composition of this coal, obviously its gas content or the residual gas content is definitely going to vary. Okay, so whenever you can see that this is your sample is not a representative of the total area, you cannot take those results into the consideration. Okay, you cannot take those results into the comparison, so you have to be very, very careful. Now again, you can take that they have discussed the proximate analysis and the ultimate analysis, and as I have mentioned that you have already read about these two, proximate and the ultimate analysis, so I am going to skip this. Okay, the proximate and the ultimate analysis detail they have discussed, I am going to skip this. Now we will be discussing with this desorption data. Okay, now desorption data, as you can see that we need the raw dissolved gas volume, as you can see from this text, raw dissolved gas volume, then the water bath temperature or the internal canister temperature, the atmospheric temperature, and the atmospheric pressure. These are to be measured very meticulously. Why temperature is important? See, there are reservoir temperature, there is a surface temperature, and there is a canister temperature. Okay, and when you are going to take that gas from the gas displacement technique by water displacement technique, then again the temperature of the gas is going to be important. Why there are so difference in temperature? Because of the different measurement and different location. But if you are not going to consider this variation of the temperature into a base, a particular base, then obviously you will be having some overestimated or underestimated data. Okay, generally the canister, the desorption canister, is to be immersed into the water bath so as to provide a constant temperature, and obviously just like the acetone test, and obviously that constant temperature should be the same as the reservoir temperature. So then obviously you can take the desorption or the dissolved gas component in the reservoir temperature only. If not, then again you have to do some calculation. Okay,
Now again, the moment you are going to put the sample into the canister, there is a internal canister volume and the internal canister temperature pressure condition. There is an external canister temperature pressure condition. The external temperature is for the water bath temperature, but the internal canister temperature may be changed. You need to record. If not, then again you have to do the correction. Okay, again you have to do the correction. So these discussions have pointed out all those sources of the error, and a closed loop is required. Again, whenever you are going to take the sample, you know that for canister you have to know this canister volume, the canister empty volume, and the canister weight, so that after you have put the sample into it, you know that how much is the void volume. Why? What is the void volume? This void volume is also called the headspace volume. This is the headspace volume they have dictated here. The headspace volume was the void volume inside the canister. That means the gap between the canister surface, canister internal volume, and the sample volume. Okay, this headspace volume is the place where the gases will be stored. The gases after desorption, it will be stored in a free phase. Okay, so if you know this volume, then obviously you will be able to understand correctly the gas in the gas dissolved volume. If not, then again you are having some error. Okay. Apart from this consideration, again the reservoir temperature. Why the reservoir temperature is coming? Because of the borehole information. You have to have the borehole information depending on the borehole depth, depending on the borehole logs, okay, and the core sample you are going to take, the core number, the depth of the sample, the density of the coring fluid and the mud fluid, what you are going to use. The reservoir information will give you the reservoir temperature, reservoir pressure, okay, and the reservoir depth. Now you must understand that there are three different gradient. Let me tell you one by one. First is the geothermal gradient, what you have read in your mine ventilation class. Geothermal gradient is the increase of temperature with depth, and this may vary from coal mines to coal mines or the coal deposits. Just like for the Raniganj, it is nearly 38 meter per 1 degree rise. Okay, 38 to 40 meter per 1 degree rise. The second is the hydrostatic gradient. Hydrostatic gradient is related to the hydrostatic pressure. That means if you increase the depth, okay, your water pressure is going to increase, and this hydrostatic gradient is considered as 10 megapascal per kilometer or 0.44 psi per feet. Let me repeat once more. It is considered as 10 megapascal per kilometer or 0.44 psi per feet from the reservoir engineering considerations. Okay. Reservoir engineering consideration is directly related to the petroleum reservoir or the gas reservoirs, and from the petroleum reservoir geomechanics consideration, they have seen it from the field studies. So this is the second one. The third gradient is for the rock density gradient or the overburden pressure stress gradient or the overburden stress gradient. This is considered as 23 megapascal per kilometer or 1 psi per feet. The rock gradient, overburden stress gradient, is considered as 23 megapascal per kilometer or 1 psi per feet. These are the records that is going to be established from the field calculations. Okay. So you can easily understand that as you increase the depth, the pressure, the effective stress between the rock overburden pressure and the water pressure, okay, the effective pressure that is going to be applicable within this area is going to be different. So that thing also you need to consider. Okay. Now, now, as you can understand, I am just going to give you the brief idea about the consideration. I am not going to have all those detailed discussion. I have taken some of the points from this discussion and I am going to give you. So don't get panicked by the all these small important discussions. Okay, these are the important because these are the sources of the error. That's why I am going to discuss with you. Now again, other than this, whatever the drilling fluid is there, okay, you know that when you are going to drill, when you are going to drill, the pressure exerted by the drill bit, okay, pressure exerted by the drill bit has to be much more, or the fluid, whatever the drilling fluid is there, the pressure of the drilling fluid has to be more than the reservoir pressure. Otherwise the rock will not break, okay. Although there is a percussion or the rotary percussion action of the drill assembly which is going to break, but when you are going to use this coring technique, okay, you cannot use the hammering, okay. So whatever the core fluid is there, the moment the core fluid, generally the core fluid reservoir pressure, core fluid pressure is much more than the reservoir pressure. If it is not, if it is less than the reservoir pressure, then obviously as the surrounding rock is having much lower pressure depending on the interaction of the core fluid than the reservoir pressure, it is going to dissolve. So the moment you are going to take out the core, it is already start resorption. Try to imagine the situation. So that thing you need to take. So you have to take out the core and you have to seal it within this core barrel. Once you put it the cover or you have taken out within this core barrel, then whatever gases are coming out due to this lowering the temperature in contact of the coring fluid, it is very much minimal. Okay, and within this core barrel, the pressure is not going to change. Now, the moment you are going to take out the surface, that is the different thing. But within this reservoir, there is no such change. Okay, because we have isolated it, and so there is a no lost gas. A lost gas, it is not going to escape into the atmosphere. So based on this, there are some corrections given. Okay, these are the some correction for disruption data. Now there are two scenarios. In this case, they have discussed the two scenarios. You remember that depending on the saturation of the reservoir, the gas saturation may be partial or it may be the total saturation. If it is totally saturated, then the moment you are going to reduce the pressure, the reservoir pressure, obviously the gases will come out. So the disruption will start out quickly. But if it is partially saturated, then you will not be able to understand when it will start the dissolve. Only after this critical disruption pressure, the reservoir pressure is going to reach below the critical disruption pressure, it will start to dissolve the gas. So for this saturation, for the saturated reservoir and for the unsaturated reservoir, they have done some consideration. You can see that these later parts, they have discussed with the saturated reservoir how we are going to take the consideration, and then the unsaturated reservoir. Okay, but believe me, the unsaturated reservoir case is much more difficult because you will not be able to consider the time when it is going to start the disruption. So the all other discussions you can skip. I have just told you very much briefly. Now next, for this calculation of this desorption or the residual gas content, obviously whenever you are going to use a direct method, this is the direct method summarizing summary. The direct method, you know that this equation you have also seen in the earlier case, and for that also, with this interpretation equation, you know that the diffusivity and the sorption time will be coming. I have also discussed the diffusivity. Diffusivity is the diffusion coefficient based on the three terms of the diffusion: Knudsen, bulk diffusion, and the intermolecular surface diffusion. Okay. So, and the sorption time is also related to the at particular temperature and pressure. The sorption time is related to the 63.2% of the gas dissolved from the coal sample. Okay. So this sorption time, with time, this diffusivity is incorporated. Okay. So whenever you are going to calculate the lost gas, you have to measure this time, because this time is going to be correlated with the diffusivity. And this temperature pressure condition, why this temperature pressure condition is much more important? Because it is observed that whenever there is a diffusivity, the rate of the disruption, okay, the diffusivity is also going to increase with temperature. Okay, it is going to increase with temperature, and you already know that with temperature the Langmuir volume, the gas storage capacity, is reduced. Okay, is reduced due to the temperature. So that's why you have to have the special care for the reservoir temperature and the pressure. So it is always mentioned that whenever you are going to do this calculation, you have to do in the reservoir temperature pressure. Okay. So in the disruption time, next is the disruption time correction. The disruption time correction is required about the first initial time when you are going to put the zero press of the stopwatch to start the time on recording. I have mentioned that the moment you are going to take out the sample from the core barrel, you have pressed zero, and within this time zero, the moment you are going to put it in your sample in the canister, you are going to seal and you are going to capture the gas. Some time is already elapsed. Okay, so you have to careful. You have to be careful for that. Again, when you have put the disruption the sample into the disruption canister, you have put it sealed, and then only you are going to put it in the water bath temperature. So the moment you have taken the sample into the disruption canister, and the moment you are going to put the sample into the water bath, and it is going to take the 30 degree or the 40 degree centigrade temperature or the reservoir temperature, there is a lapse of time. So that correction also has to be made. Okay, the exact timing is very crucial. So this correction, or what are the problems are arising with this correction, they have discussed here. And lastly, the direct method calculation, as I have mentioned in the earlier class also, there are two variations. Direct method we have seen already by the pressure cooling technique, or this then direct method was for the resorption canister, what we have just discussed. There are two variations of the direct method. One is the Smith and Williams method, and another one is the Amoco method. In the Smith and Williams method, most of the items are same, assumptions are same. Only the difference is that they are going to use a volume correction factor. Volume correction factor to a loss time ratio, okay, loss time ratio and a surface time ratio. That means time when you are going to see the lost gas, that some amount of the gases are already lost, and it is going to be taken to the surface, the core should be taken to the surface. Okay, this ratio from the initial time, they are Can you hear me? Sorry for the disturbance in between. So and for that correction factor, they are going to consider the surface time ratio and the loss time ratio. Okay, the ratio. And it is observed that whatever gas content they have calculated by this method, it is somewhat lower than the direct method. It is somewhat lower means it is 27.3% lower. So it is 1/3 ratio. So significant error is there. It is underestimated. The result is underestimated. Whereas if you see the Amoco method, in this Amoco method, they have taken the simplified form of the direct method equation. They have considered the nonlinear regression equation. In the direct method, we have taken the extended backward in the linear direction to get the initial gas loss gas content for the time calculation. But here in the Amoco method, they have considered the lost gas consideration by nonlinear regression. And it is also to the diffusivity is also related to the sorption time and the gas totally dissolved. Okay, and this diffusivity will give you the idea Now again to see this calculation based on this Amoco method. You can see when we are going to see this Amoco method, we are going to based on this calculation based on this three parameter: the loss gas content, the total gas content, and diffusivity, which is going to take the absorption time. And obviously the results are higher. The results are higher. How much higher? It is the 21% greater. So 1/5 higher results are over is not preferable than the direct method, and the direct method is the universally available method, is the only universally available method to calculate the reserved gas and the loss gas component. So, and in this chapter I would like to say that you please go on the salient features about the error and the considerations. They have also shown you some examples. You may skip that, or if you may want to study to clear your understanding, you can study. But I am very much related. I am very Any questions you are having?